Welcome back, welcome back, welcome back. I'm Miss Lisa. This is physics class where we are talking about motion in two dimensions and projectiles. This is chapter 7, part 2. So if you haven't watched part 1, you might want to watch it first. Or if not, you might want to just learn about the motion. What it's talking about with this motion in two dimension is projectiles. Things that are, this is some water shooting out and it's going down. And what we're going to do in this is we're going to talk about the math. That's the picture I told you about in the other one where the X and the Y are independent. And if you throw a basketball or drop it, they're going to hit at the same time. Okay, so in this, on page 135, they talk about the formulas for the Y component and the X component. And that will make more sense when we do a real problem. All right, so we're going to start with problem 1. On page 136, and feel free to stop it and try it on your own calculator as we go through the steps. Okay, it says, a stone is thrown horizontally, you can see it right here, at 15 meters per second from the top of a cliff, 44 meters high. A, how long does the stone take to reach the bottom of the cliff? Okay, now I actually did this twice. Let's see which one I think looks better. I think this one does. Okay, so first you list your knowns and unknowns and draw a picture. So my height is 44 meters, and that's the Y component. Then the other thing is it started with its initial velocity. The book calls it velocity Y. I think that's confusing. I like velocity I. The initial velocity, how it started, was at 0. It hadn't sped up any. At the very beginning, it was at 0 for the Y component. Its X component, it had a velocity. It was going out this way. But Y, it had not gone down for just a tiny second when it started. You can think of it like, you know how the cartoons run off the cliff and then they don't fall until they realize it? There's that split second before it starts falling there, and where it's at 0. The acceleration due to gravity is 9.8 meters per second squared. So, and we know that the velocity in the X direction is 15 meters per second. And what they want to know is how long will it take to get there? So I think, is there a formula that's got time in it that I've got everything else for? And there is. It's this. The height or the Y component is equal to the initial velocity, which is 0 times time, plus 1/2 gravity times time squared. Because this is 0, anything times 0 is 0, I can just ignore that part. And a lot of times in these problems, you get to skip that part because your initial velocity is 0. So there it is, what's left of it. And I've got Y is 44, a half is a half, gravity is 9.8, and time is what I'm solving for. So I'd go ahead and start doing it like this. And I would do 44 divided by a half, divided by 9.8, and then take the square root, and because I don't want time squared, I want time, and the opposite of squared is square root. I take the square root, and I get that it's about 3 seconds, okay? I did it again over here, and I don't know, maybe I like it better in black than purple. All right, so let's see our next question. B, how far from the base of the cliff does the stone strike the ground? So now we want to know how far out this goes. We can't just look at this graph because they drew the graph at the end. So that'd be cheating. But we can kind of tell from the graph it looks like it's going to be 45. We have to use our math though. Okay, so this is our formula. For the X component, it's the speed of X times the time. And they told us the speed of X was 15 meters per second, and we just figured out that the time is 3. So 3 times 15 is 45. And the third thing they said was draw a picture of it. Now, I would always draw a picture first and then fill in what I know. So I would fill in that I would make it where that's 45 and stuff like that. All right, next problem. That was number 1. Here's number 2. In the strobe photo, the flight of the ball is the flight of the ball. So these are being taken at equal time intervals, but you can tell where it's going faster or slower by how spread out it is. The initial velocity of the ball was 4.47 meters per second at an angle of 66 degrees. So it was 4.47. Oh, let me get my picture. 4.47 at 60 degrees. It's got an X component and a Y component. Okay. Above the horizontal. Find first how long it took the ball to land and how high the ball flew and what the range was. Okay, so that's what we know so far. And using our trig that we learned last time, we know that if we want the Y component, it would be the opposite. So some old horse, the sine is Y over the hypotenuse, and cosine is X over the hypotenuse. Which is the adjacent. So caught another horse. Some old horse caught another horse. All right. So let's look at the problem. Okay, so we know the formula for X. We know the formula for Y. We know the initial velocity. We know the theta. We don't know the time. We don't know the distance. So the distance is the Y going up. I think they're going to ask us for some more stuff. How long, how high it flew, and what its range was. So that was the other one, the range. All right. So this formula, the velocity of X equals the initial, the velocity, our velocity here, times cosine of theta. So this is where we're getting our X. We're going to multiply both sides by the hypotenuse. So hypotenuse cosine theta is 4.47 cosine theta. And so our X velocity is 1.82. Let's see where they've got that written. It's right here. So that's what they did first there. It's 1.82 meters per second. But that's how I think of it. Okay? So then to get the Y, we're going to do this. So it's going to be the sine for the Y, which is going to be 4.47 sine 66, which is 4.08. So, back over here, our theta is 66, our hypotenuse is 4.47. To get this out of the denominator, we do the opposite. So we multiply both sides by 4.47, so it's going to be 4.47 cosine 66. And that is how we get that one. So both of those get put in like that, and we got the right answer. It is 4.08. So we have the X and the Y now. All right, next, okay, so now for A, they want to know when it lands, the height. We know that the height is 0. So the Y part, the final part, Y equals 0 at landing. So we can fill in our formula that we had before, and we can put in 0 for Y, 4.08 for our V sub Y, which we got right there, and then we do plus 1/2 the pull of gravity times time squared. So we have everything but time, and we can solve for it. So you just keep working it all out until you get the time is 0.833 seconds. I guess I should show you how, step by step, how I do this. Okay, so it's all here, and I need this, I need that all, I needed to put that on, TT. Okay, so let me show you. Sorry about that. I wanted to make sure I said it clearly. So, okay, here's our original equation. So the first thing that I did was, this has a t, and that has t squared. So to get my t's together, I factored a t out. So I pulled a t out, and I put it right here. Then I divided both sides by this t. Well, 0 divided by anything is 0, and that makes that extra t go away. Isn't that useful? Okay, now I can start solving for it. So you always work from what's further away from what you're solving for and then to what's closer. And you do the opposite. So this is a plus 4.08, so I'm minus 4.08 from both sides. And then I divided both sides by 1/2 and 9.8. So, and then that's t. And I sort of wrote it here. What I would normally do is just sort of do it on my calculator, but I wrote it all out there. To divide by 1/2 is the same thing as to invert and multiply, so you could put a 2 here, or you could just on your calculator do your number divide by 0.5 divided by 9.8. And because it was down, it's negative, and that makes our negatives go away. And you know that time always has to be positive. So our time is 0.833 seconds. Okay, so for B, it says the maximum height occurred at half of the time of flight. So if this is the time, 0.833, the maximum height is right here at half of that, 4.17 seconds. So you take your time, divide it in half, and then you've got the maximum height. So now, so we took our time, divide by 2 to get the maximum height. And now we got it right here. Now we're going to put that time in here, and we're going to solve for the what that is. What is this maximum height? What is this y here? So we're going to use that equation again. So our v sub y, our speed, our velocity is 4.08 times our time, 0.417 plus 1/2 times gravity, and we're going to times 0.417 squared, and we get that our y is 0.85 meters. So that ball didn't go up very high. And we can see that we got it right. Yay. All right, and then the range. I didn't think I did the range. A, B, I don't see C. Here's the range. The range is the horizontal distance traveled during the entire flight time. So you put it into this formula for the range. So it's 1.82 times our time, 0.833, the whole thing. And it is 1.52. So that one's not too bad. And where we got that 1.82, in case you forgot, it was one of the first things we solved for, which was our v sub x. All right. So try all of these yourself. Do that lab. Do the softball lab. Here is problem number 3. A 0.13 kilogram rubber stopper is attached to a 0.93 meter length of string. The stopper is swung in a horizontal circle, making one revolution in 1.18 seconds. So that's our period. Find the speed of the stopper, find its centripetal acceleration, find the force the string exerts on it. So I want y'all to do this lab. We did it last year. What we did last year is we took something on a string, I don't remember what it was, and we swung it around and we tried to hit a tree, and it was very fun. See, I made a note. Very fun. So I want you to do that lab too. A lot of these pocket labs are really good, and there's stuff that's just around, and you should try to do them all. They're really fun. All right, so this is what we know. We know the mass is, so because remember, we always list our knowns and unknowns first. Our mass is 0.13 kilograms. The length of our string, by tradition, written in cursive, equals 0.93 meters. Our period is 1.18 seconds. So our formula we're going to use is the velocity, or speed, equals distance over time. The distance, that is 2 pi radius, because we're going in a circle, and the time is the period. So it's 2 pi 0.93 divided by 1.18, our period, and it tells us that is 5.0 meters per second. Okay, so for B, Our acceleration is velocity squared, centripetal acceleration, velocity squared over the radius. So we figured out that the velocity was 5, so we're going to do 5.0 squared. And the radius we figured out, it was given to us, the length of our string is 0.93. So we just square that and divide it, and there you go. 27 meters per second squared. For C, they want the force, and force equals ma. That's our famous formula. And the mass, we know it was given to us. And the acceleration we figured out. So we just multiply them together and we get the force, 0.35 newtons. So there you go. Radially inward. So that's why it says in here. That it's, and you can read about why that's inward. Okay, so then we talked about this. Okay, here's our next one, a pendulum problem. Okay, so I'm going to read it and you can look at the notes while I do that. On top of a mountain, a pendulum 1.55 meters long has a period of 2.51 seconds. What's the acceleration due to gravity at that location? So normally that's 9.8. So we know we should get something close to 9.8, but not 9.8. There's less gravity the higher up you go. So it should be less than 9.8. So we fill it into our formula, and this is our formula. It's right here. The period is 2 pi times the square root of the length of the string times the absolute, divided by the absolute value of the acceleration due to gravity. So we have everything here and we can just fill it in. The period is 2.51. 2 pi, 2 is 2, pi is pi. On your calculator, how you get to pi is it's the second of the up arrow. See that little pi right there? All right, times the square root of 1.55 over x. So how I would do this on my calculator is I'd first put in 2.51. Why don't we do it together? Okay, turn our calculator on, and I start here with that, 2.51, and then I'm going to do the opposite to try to get x by itself. So I'm going to divide, this is being multiplied by 2 pi, so I'm going to divide by 2 pi. So I do, and I usually do divide by 2 and then divided by pi. So second up arrow is pi. Okay, next, this is under a square root. So to get it out, to get rid of that square root, that's what's making it ugly, I do the opposite, and the opposite of square rooting is squaring. And that will, if I square this side, it will free it, so I need to square this side. So this button right there, that x squared, I press it, and that, now this is all freed up. And so I would multiply each side by x and then divide it by what I have. So I'm going to be dividing 1.55 by that. So I'm going to do 1.55 divided by, and I'm going to just copy it down, 0.15, and I'm going to use a bunch of these because, you know, I don't want to get the wrong answer because I rounded too much. The way you're supposed to do it is you use as many significant figures as you can in your calculation until the very end, and that's where you round. And I got 9.71. That looks good. It's less than 9.8, but not too much less, and it's what they got too. Yay! Go me, I got it. You can see how they did the math a little bit different than me. I like my way. You can do whichever you want. You don't even have to tell me if you do it a different way. All right, so that's this chapter. I think it's fun. Read through it. Read it carefully. Do the assignment. Assign you the problems that have the answers in the back. So do a problem, check it. Do a problem, check it. The purpose of homework is to learn. The purpose of the test is to test you. So I always try to make it where kids can check their answers as they go so they get good doing the homework and then they do great on the test. All right? Math is fun, physics is fun, science is fun. Like, share, subscribe, and I'll see you next week.